Welcome back. In this video, we'll talk about how to evaluate a linear regression model and see whether or not it's really doing a good job describing the relationship. So we'll talk in this video about how to do statistical inference on the regression coefficients, beta 0 and beta 1. We'll also introduce some assumptions that we make when we do regression, or some conditions that should be satisfied. We'll then talk about some visual tools that we can use to evaluate a regression model. So let's begin with some conditions on our linear model. So there are 4 conditions that a linear regression model must satisfy. Conveniently, we can write these with a nice little mnemonic. These are the line assumptions, or the line conditions. First, the L condition. X and Y must have a linear relationship. It doesn't really make sense to use a linear model to describe a non-linear trend. Second condition, the I condition. The individual observations and therefore the residuals must be independent. So there should be no linkage or no connection between our observations. Third condition, the N condition. The residuals must be normally distributed with mean 0. And then finally, the E condition, the errors must have constant variance. So let's start with looking at the L condition. How well, for example, does the linear model fit the brain empathy data from the previous video? Here we're looking at a larger version of this data set. As a reminder of the experiment, we had couples in a committed relationship where the female partner completed an empathy test and then watched her male partner receive a series of electric shocks. The brain activity is measured as a fraction of the activity that she felt in the pain centers while experiencing the shocks herself. In general, we can see is that as this empathy score is increasing, so is the brain activity. It's doing so in a roughly linear way. So that L condition looks like it's met. Let's talk about the I condition, or the independence condition. Here we ask questions like, where did the subjects come from? Are they reasonably independent in terms of being a random sample? Are there any reasons for the observations to be correlated? So for example, did we do this experiment on the same subjects multiple times? Did we select people who had some shared characteristic? And so on. So is there a reason in terms of the study design for the observations to be independent or dependent? Now, before we talk about the final 2 conditions, the N and the E condition, let's talk a little bit about the model summary and what information we're getting from that, because that can help us assess these conditions. So here I've fit my model in R, again using the LM function, LM standing for linear model. We write that brain activity depends on empathy, so that's what the tilde represents. We can then use the summary function to help us get some more information about this linear model. Now there are 2 tables that we want to look at in this summary, the residuals and the coefficients. Focusing in on this residual table. What's reported here are summary statistics for the residuals, so what values the residuals take on. So for example, the median residual is negative 0.006. That should be close to 0 if these are normally distributed with mean 0. If the residuals are normally distributed, the quantiles should be similar as well because the normal distribution is symmetric. So the absolute value of the first quartile, here written as 1Q, should be similar to the absolute value of the third quartile, here written as 3Q. So those are the kinds of things that we look at in the residual table to check to see if our model fit is reasonable. The next table that we want to look at in the summary output is the coefficient table. Now we get a lot of information here. We get the estimates, so we have the estimated intercept, the estimated slope coefficient. We get the standard error of our estimate. We get a t-value, so maybe we're doing some kind of t-test. And then we also get a p-value, so we're definitely doing some kind of test here. But what test are we doing? How do we know whether our model is significant? Well, let's think for a minute conceptually about what would happen if there were no relationship. So let's say that as x is increasing, there are no changes in y. We essentially have a flat trend. If there's no relationship or a flat scatter plot, then we would expect that slope coefficient, beta 1, to be 0. So it looks like we might be testing, and in fact you can verify this by calculating the t-statistic using that standard error. Here we're testing whether or not the slope coefficient is equal to 0. If the slope is equal to 0, then there's no linear relationship. If the slope is non-zero, then there is a linear relationship. That's our alternative. So here, this p-value on empathy is very strong. That indicates that there is strong evidence that the slope is not 0. There's strong evidence of a linear relationship. Now, let's take a look at those last two line conditions, the end condition and the E condition. Here we can use some scatter plots of the residuals to take a look at these conditions. So the first plot that we'll look at is a scatter plot of the residuals against the fitted values. So this plot will have the predicted values y hat on the x-axis, and on the y-axis, what you'll see are the residuals. What you'd like to see with this is something like plot A. You want to see no trend, random variation above and below 0, usually indicated with a line, no pattern, no runs, kind of a horizontal band or a cloud. Plots like B and C, if there's some pattern here, that indicates that we might not have constant variance, or that there might be a pattern in the data that we're missing. In order to generate these plots, we'll use a function in R called plot. We'll just simply generate a plot of our model. This will actually produce 4 plots. We really only care about the first 2. So the first plot looks a little bit like this. This is a plot of the residuals against the fitted line for the brain activity data set. So we have the predicted values on the x-axis and the residuals on the y-axis. This is a great example of what this plot should look like if a linear model is appropriate. We see a roughly horizontal trend indicated by this red line. It should be pretty close to the gray dotted line, which is 0. We also don't really see any increase in the variation. The points aren't becoming more or less spread out, just a fairly constant band. So this is good. This is what we'd like to see. In order to evaluate the N condition a little further, the normality condition a little further, we'll use a normal QQ plot. So this plot can be used to check to see whether or not the residuals are normally distributed. We've looked at similar plots before. What you want to see here are most dots close to the diagonal line. There might be a few deviations from that diagonal. If there are, we'd like to see them at the end. So this is an example of a pretty good looking QQ plot. There is a little bit of wiggle. It's not perfect on the line, but overall, if you were to stand across the room and look at this plot, you would say, hey, that's a pretty straight diagonal. There's nothing too obvious here. The next thing that we might want to look at when we're evaluating our model is whether or not there are any outliers or unusual values. So an outlier is a point that stands away from the pattern of the rest of the data, so it's pretty far in regression from that linear trend. We care about outliers because these can have pretty strong effects on the linear regression model. One thing that we often get calculated for us are, instead of actual residuals, something called standardized residuals. In fact, you can see them on the y-axis here. What those standardized residuals represent are the actual observed residuals minus the mean of the residuals divided by the standard deviation or the standard error of the residuals. Essentially, we're just calculating z-scores on these residuals. So these standardized residuals are not the residual value themselves, rather they're z-scores. Now, how we might know if there's an outlier one thing we can do is add labels in our plot for each observation, so we can actually tell which observations are unusual. Here I've done this by adding a label geometry, so you can see highlighted in yellow I'm using geom_label. My labels are the row names of the brain empathy data set. It looks like observation 36 is much higher than the linear trend in terms of brain activity. Observation 48 is a bit higher than the trend as well. So those are observations that will probably have large residuals that we might want to take a look at. Now, the final thing I want to talk about briefly in this video is what can happen if we make predictions where we shouldn't. And we call that extrapolation. So extrapolation occurs when we use the regression line to predict beyond the range of our observed data. This can be dangerous for a lot of reasons. The major reason that we might not want to do this is that there's no guarantee that the trend will continue. We haven't actually collected any data, so we don't know whether the trend will hold. So for example, if we take a look at a subject whose empathy score is 0, let me go back to the slide previous to show you that the lowest empathy score we observed was around 20 on this inventory. If we predict the brain activity for a subject with empathy level 0, what we end up getting for our slope is, or for our intercept, is a negative level of brain activity. So we would actually predict that this subject's brain would shut down. They would have a negative brain activity response as a proportion. So we would get a prediction that's mathematically and conceptually invalid. Doesn't make a lot of sense. In the next video, we'll talk about how to extend this regression model to the case where we have multiple explanatory variables. I'll see you then.